Hello everyone. Welcome to another revision lesson in cubic functions. So, kule video we'll just discuss the solutions to this question, right? So lana we have this graph, and then but the graph of the function f is sketched below, and then first question they want us to calculate the coordinates of the turning points of f. I think we should be able to do so if we all know how to differentiate using the rules of differentiation, right? So if you are given a cubic function and then you are being asked to calculate the turning points or stationary points, you should know that at some point there you need to differentiate, right? So because the whole purpose of differentiating is to calculate the gradient of a function at a point, right? So now if we want to calculate the turning points, we know that at the turning point the gradient of that function should be 0. Therefore, if we equate the first derivative of this function to 0, that will give us the turning points where the gradient is 0. The gradient is 0 because if you draw a tangent to this point, which is a turning point, you will see that tangent will be will be a horizontal line, and then we know the gradient of a horizontal line is 0. So that's why when we find the turning points, we equate the first derivative to 0, right? Okay, so we will go ahead and do that. So 9.1.1, we want to calculate the x-coordinate of the turning points of f, so we need to differentiate, right? And then we differentiate our function using the rules. So there we will have minus 3x squared minus 2x plus 16, right? So this will be our first derivative of that function. Now to calculate the turning points, we will need to equate this first derivative to 0, right? So this will give us the x coordinates where the gradient of the function is 0, and that corresponds to the turning points, right? So if we do this, we indicate if we say first derivative equals to 0, we are indicating we want to calculate the x coordinates where the gradient is 0. And then it turns out at the turning points the gradient will be 0, because if you draw a tangent to that point, it is a horizontal line, and then the gradient of a horizontal line is 0, right? I hope that makes sense. So now if I equate my first derivative to 0 and solve for x, I should get the x coordinates of the turning points, right? Plus 16 equals to 0, and then I will divide throughout by a negative. I will have 3x squared plus 2x minus 16 is equals to 0, and then I'll factorize. Here I'll have 3x plus 8 multiplied by x minus 2 equals to 0, and then my x coordinates of the turning point will be x equals to minus 8 over 3, or x equals to 2, right? So the point minus 8 over 3 will correspond to that turning point. So here our minus 8 over 3 will be here, and then this turning point will correspond to the x value of 2, right? Okay, and then Siago 9.1.2 9.1.2, they want us to calculate the x coordinate of the point at which the first derivative is a maximum, right? So notice the first derivative of our original function is also a function, right? And then we see our function is a cubic function, and it is sketched here, and then the derivative of this function is a function itself, which is a parabola or a quadratic function, right? So now on this question, they want us to calculate the coordinates of the point at which this function has a maximum, right? Now we know what the coefficient of x squared determines the shape of the function. So we see within the coefficient of x squared is less than 0. Therefore, the graph of this function will have that shape, right? And then Tina, we are interested in the point where this graph is a maximum, right? So which is a turning point. So if you know how to calculate the turning point of a quadratic function, you should know what this will be x equals to minus b over 2a, where b is minus 2 and a is minus 3, right? So you will have your x coordinate to be it will be minus 1 over 3, right? Alternatively, you can calculate the second derivative of that function and equate it to 0. So let me do that and show you. So if we calculate the second derivative, it means we are taking the derivative of the first derivative. So second derivative, I will differentiate this function, right? So my second derivative will be equals to minus 6x minus 2, right? And then if I equate the first derivative to the second derivative to 0 and solve for x, I'll get the point where that graph has a maximum, or where the gradient of the tangent to that point is 0, right? So I'll have minus 6x squared minus 2 equals to 0. And then if I solve for x, I see what the x is equals to 2 over minus 6, which is minus 1 over 3. So you can do it this way or that way, right? So we are done with 9.1. We can move on to 9.2. I'm just gonna erase here. Okay. So, okay, 9.2. 9.2.1. 9.2.1, they want us to determine the equation of the tangent to the graph at x equals to minus 1, right? So again, we need to differentiate, right? So the whole point of differentiating is to calculate the gradient of this graph at a specific point. So now, to calculate the equation of the tangent, or to determine the equation of the tangent at this point, we will first need to know what is the gradient of the function at that point. So at x equals to minus 1, the gradient of the function should correspond to the gradient of a tangent that is passing through that point, right? I hope that makes sense. So at x equals to minus 1, we want the gradient of this function at x equals to minus 1, right? So to do that, we'll need to differentiate this function f prime g prime x equals to minus 4x minus 9, right? And then now to determine the gradient at x equals to minus 1, I'll substitute minus 1 in this first derivative, right? If I say minus 1 there, I'll have minus 4 minus 1 plus 9, and I'll get my gradient to be minus 9 minus 9, and then here I'll have plus 4 minus 9, which is minus 5, right? So g prime at negative 1 is minus 5. So therefore the tangent that passes through the minus 1, the tangent to this function g that passes through minus 1, x equals to minus 1, will have a gradient of minus 5, right? So I'll have y equals to mx plus c as the equation of my tangent, because it is a straight line, right? So m is the gradient, which is minus 5, the minus 5 we just calculated there, right? So now my equation will become y equals to minus 5x plus c, right? So now I need to calculate the value of c. In order to calculate the value of c, I will use the same point minus 1 and see if x is minus 1, what is the value of y in that function, right? So I'll substitute minus 1 into my function, right? And then I'll have minus 2 times minus 1 squared plus minus 9 times minus 1 plus 5, right? And then if I just punch into my calculator, I'll get to when x is equals to minus 1, y will be 12, right? So therefore I can use this point or this coordinate minus 1, 12 to calculate the value of c, right? So now if I go back to that function there, and where I see y I put 12, and then where I see x I put minus 1, I can then solve for c, right? So c will be equals to 12 minus 5, which is 7. Therefore the equation of my tangent will be minus 5x plus 7, right? And then you are done with 9.2.1. okay, let me erase here and create space. So 9.2.1, our equation of the tangent is y equals to minus 5x plus 7, right? So 9.2.1, our equation of the tangent is minus 5x plus 7, right? And then 9.2.2, they want to know for which values of q will the line with y equals to minus 5x plus q not intersect the parabola, right? So if we sort of like draw a rough sketch of that parabola, we know it has a y-intercept at 5, that will be somewhere there, and then it has a turning point at x equals to minus b over 2a, where b is equals to minus 9, and then a is equals to minus 2. So this will be minus, but 9 over 4, right? And then we know that will be somewhere here, and then our turning point will be, if you substitute minus 9 over 4 into the function of g, uzoba no minus 2 times minus 9 over 4 squared, minus 2 times minus 9 over 4 squared, minus 9 times 9 over 4 plus 5. You'll get the turning point will sort of be minus 9 over 4 and 15.125. That will be somewhere there. And then we know our x-intercept will be on our x-axis, right? So this function has this shape, né? Now they want to know where does the line with this equation minus 5x plus q won't intersect the parabola. So if you go back to 9.2.1, the tangent intersects the equation of the tangent, this tangent that we calculated intersects the parabola at x equals to minus 1. So that will be somewhere there. So somewhere here we will have our tangent, right? Somewhere there it's our tangent. It intersects the graph at x equals to minus 1, right? And that tangent intersects the y-axis at y equals to 7, ne? So now notice the line y equals to minus 5x plus q has the same gradient of minus 5. It has the same gradient as the tangent line, the gradient of minus 5. So these two lines are these two lines are parallel, ne? Okay, let me go back to my sketch. So these two lines are parallel, which means that in order for this other line y equals to minus 5x plus q not to intersect the parabola, it means our value of the y-intercepts needs to be greater than 7, such that our line will sort of be above the tangent line, right? So the value of q, the values of q for which this line won't intersect the parabola is q greater than 7. Because if q is equals to 7, we will come back to this tangent line which intersects the graph at x equals to minus 1. And if q is less than 7, we'll sort of like have lines looking like this, which will intersect the parabola at some points. So the lines that we want are the one that won't intersect the parabola. So that line has the same gradient as the tangent line, but then the value of the y-intercept has to be greater than 7, which is why we're saying q has to be greater than 7. Okay, I hope that makes sense. And then going on to 9.3. So lapho 9.3 we are given h of x is equals to 4x cubed plus 5x, and then they want us to explain if it is possible to draw a tangent to the graph of h that has a negative gradient, and then show all our calculations, right? So now we know that in order to find the equation of a tangent, we need to first calculate the gradient, and we do so by finding the first derivative of that function, right? And then if we calculate the first derivative of that function, we'll get what we'll have h prime x is equals to, the first derivative of that will be 12x squared plus 5x, right? So this is sort of like a function which we will use to calculate the gradient at specific points for this function, right? So now notice ukuthi 12x squared plus 5x will always, 12x squared plus 5, not plus 5x. So that is 12x squared plus 5 will be our first derivative, right? So notice ukuthi 12x squared plus 5 will always be greater than 0 for any value of for any value of x, for any value of x, right? If you pick x equals to minus 1, you'll have 12 plus 5, and the answer is greater than 0. If you pick x equals to 10, you'll have 120 plus 5, and the answer is always greater than 0. If you pick any value for x, this function will be greater than 0 for any value of x that you choose. So because this is greater than 0, it means the gradient of this function at all the points will always be greater than 0, meaning this function is an increasing function for all values of x, right? So this is an increasing function for all values of x. Now because it is an increasing function for all values of x, we cannot draw a tangent which has a negative gradient kule function le, because the function is always increasing, right? So a tangent line with a negative gradient won't be possible for this function, right? So we can go ahead and conclude, therefore it is not possible to draw a tangent with a negative gradient, right? That is how you conclude. Okay, so with these questions, I mean, all that you need to know, what is the meaning of the first derivative, what is the meaning of the second derivative, how to calculate the first derivative, how to calculate the second derivative, right? So if you know the meaning and how to calculate those, any question you can answer, because it's just an application of calculating the first and second derivative, right? So if you question a challenger, try to go back to the basics like all the time, ne uzama ukwenza i-sense of these kinds of questions, because see, masicala i-calculus, we spoke about the derivative and what does it mean. So sikhulumile ukuthi derivative is just another fancy way of calculating the gradient. That's all that we're doing. We are calculating the gradient of functions at specific points, right? So a gradient of a straight line, we know ukuthi it is constant, but a gradient of a curve like this, it is not constant, because the curve has the tangent lines to these curves will have different tangents, or will have the different gradient or slopes at all the points, right? But a straight line has a gradient which is constant. So calculating a derivative is a way of sort of trying to determine a gradient of a curve at a specific point, right? So if you know a gradient of a curve at a specific point, you can be able to calculate the equation of a tangent that passes through that specific point, because it will have the same gradient as that curve, right? Okay, I hope it makes sense. If it doesn't, you know, I'm always available to answer any questions. So if you're still confused, alright, so this will be our last lesson for calculus and cubic functions, and then after this we will go on to analytical geometry, and then after analytical geometry we can look at Euclidean geometry. So after this we'll sort of like try to wrap up we sort of like wrapping up the revision for paper 1 with this video, and then from Monday onwards sibheka i-revision in paper 2, analytical geometry, and then Euclidean geometry. Okay.